Hi everyone. I don't think I mentioned the other day in class, but right now, as of right now, I'm at Gustavus Adolphus College in Minnesota. No doubt freezing right now, but I'm about ready to give a talk this evening, which is why I'm not in class today, and which is why we took the step of me recording a very brief lecture as an introduction to mathematics and design. And as soon as you're done watching this video, Darwin and Joseph will play another video that I will want you to watch as part of this lecture, and then we have a design exercise after you've watched both the lectures. The first thing I want to, the first idea I want to introduce you to is the notion that mathematics is actually the study of pattern. If you talk to mathematicians, they will tell you that while we study numbers and calculation and these sorts of things, at its heart, mathematics is really the study of pattern. And it turns out, of course, that there are all kinds of patterns in nature, like honeycombs and snowflakes and rings around trees. And it turns out a lot of these patterns in nature have mathematical structures to them. And mathematicians over the centuries have been able to identify a lot of these mathematical structures. Here's the first one I wanted to show you, and if you've studied mathematics, maybe you've encountered the Fibonacci sequence before. The Fibonacci sequence works like this. You take the number 1, add 1 to it, and you get 2. And then you take 1 and 2 and add those together, and you get 3. You take 2 and 3 together, and you get 5. You add 3 and 5 together, you get 8. 5 and 8 together, 13, so on and so on and so forth. That's how you get the Fibonacci sequence, and that's the first few numbers in that sequence. Well, it turns out that that sequence of numbers turns up in a lot of natural phenomena. Like, well, before I get to that, let me show you this. If you take the square, if you square, literally make squares out of each one of those numbers and arrange them like this, you get this sort of shape. And then if you connect all of those Fibonacci squares together, you get this sort of swirling pattern. And this, you've probably no doubt seen in like nautilus shells, for instance. And that follows a kind of a Fibonacci pattern, a Fibonacci swirl. It's what that's called. The Fibonacci numbers, the Fibonacci sequence appears in lots of other natural phenomena. We're looking inside a sunflower right now. And if you look at the pattern, the way in which the interior of the flower is arranged, it has that sort of pattern. Well, it turns out that the numbers inside sunflower are in the ratio of 34 to 21, which is this ratio right here, 1.61, repeating, repeating, repeating. We're going to come back to that in just a moment. Look inside, hold a pine cone in this direction, and again, you see similar sorts of patterns. In this case, it's 13 and 8, and you get this number 1.625. Both of those numbers are close to, and eventually will approximate, this number right here, which is called the golden ratio, or phi, It's represented in lots of different ways. Linearly, it's the ratio of A plus B. A plus B is to A as A is to B. And that ratio is 1.61, repeating, repeating, repeating. And if you put it as the golden rectangle, it's called, it's this sort of ratio here. There's A to B is to A as A is to B. And that's how we get this repeating golden ratio. We find it in the natural world. We find it, as I say, in sunflower, everything from sunflowers, nautilus shells. But we've also used that principle as a way to design some of our structures as well, as we'll see here in just a moment. Here's some more images of this, more images of the golden ratio. And again, here you see the relationship between that swirl and the golden ratio. Some other ways of depicting it. We talked Tuesday, we talked about bricks, and I made very brief mention that bricks pretty closely approximate that ratio, 1.61, or that golden ratio. And it's something that we see again and again in lots of different civilizations. Whether or not they understood the mathematics of this, there is something about that ratio that we find repeated again and again in human design. There are those that suggest that it's a more pleasing sort of ratio than other types of shapes and structures we might find. I think the Greeks were probably a little more deliberate about this, and in all kinds of structures. The Parthenon, we'll see more examples of the Parthenon later on. But it seems to follow that golden ratio. It seems to follow that constant phi. I want to introduce you to another set of geometric shapes, and this will form the basis, the background of the video that you're going to be watching from Ron Eglash. But I want to look in particular at fractals. And a fractal is defined as a shape or a structure that exhibits self-similarity across scale. And again, we see instances of this throughout nature. So ferns, for instance, are self-similar across scale, which means you look at a fern as a whole, you zoom in one of the branches, and the branches looks like or is similar to the larger structure. Then you zoom in on some of the fronds, and they look like the branches, which looks like the larger structure. Cauliflower is self-similar across scale. Trees, branching trees, you can look at the whole tree, zoom in on a branch, zoom in on twigs. They look the same. There's a self-similarity across scale. The bronchia in our lungs, for instance, are also something that exhibits fractal self-similarity, as do coastlines, right? We're obviously looking at something at an aerial distance. If you were to zoom in on one of these tributaries, we would see the similar pattern repeating itself, even right down to creeks and other sorts of smaller movements of water. This is what we mean by fractal shapes, self-similar regardless of the scale. That's a pretty good definition of fractals. We see fractals in nature all the time. The mathematics of fractals really weren't understood until the 1980s. And it was this guy, Benoit Mandelbrot, who helped us understand the mathematics of fractals. I'm going to give you a very, very quick mathematics lesson here in the mathematics of fractals. Mandelbrot started with this constant, z equals z squared plus c. It's a fairly simple sort of equation, probably even simpler than what you'd find in a basic algebra class. What we're going to do, though, is focus on the z term and the c term. We're going to plug in values for z and for c. What this particular type of equation is called a recursive equation. So in other words, what's going to happen is the result that we get by plugging in some numbers, we're going to take that result and plug it back in the beginning. Okay? So what that, in this case, so for instance, we're going to set z equal to 0 and c equal to 1. C is a constant. We will keep that number constant throughout this pattern. So when you have z equals 0 and c equals 1, and you run the equation, you get the answer 1, right? So 0 squared is 0 plus 1 equals 1. Now we're going to take that 1 and plug it back here in the beginning as z. And so you have 1 squared plus 1 is 1 plus 1 now equals 2. Now we're going to take that 2 and plug it in back at the beginning so that z equals 2. And so 2 squared plus 1 equals 5. And then we're going to take the 5 and plug it in, and that gets 26. And we're going to take 26 and plug it in, and that gets us 677. And we're going to plug it in over here, and we're going to get 458,330. And very quickly what you're seeing is that number is going to go off to infinity pretty quickly. Keep that point in mind. Depending on the numbers that you plug in, how quickly do the equations race off to infinity? If we set the constant at 0, well, it kind of stays put, right? 0 plus 0 equals 0. And we have something that just sort of doesn't recurse very quickly at all. What if we set z at 0 and c as negative 1? Well, then you get, in the first instance, you get negative 1, and then you plug that back in, and negative 1 squared equals 1 minus 1 is 0. So you plug that back in, and you get negative 1, and this just goes back and forth between 0 and negative 1. It just goes back and forth, back and forth, back and forth. You can represent this graphically. So if you set c equal to negative 1.1, this is where the numbers sort of go back and forth, right? If you set c to negative 1.3, you get that structure. If you set c to negative 1.9, you get that weird structure. There's c at negative 1.85. You can take that c number, it's just a regular number, and plot it on a number line like this. What Mandelbrot did was to take that whole technique, and instead of using regular real numbers, use something called complex numbers. And that's all a complex number is. All a complex number is. It's a real number, a, plus another number times I. Another number times I. And I is called an imaginary number. It's represented as the square root of negative 1. It takes its own kind of timeline. to represent it. In fact, it's not a timeline at all. It's more like a space like this, with the A number along this axis and the B times I number on this axis. So here's how you plot those complex numbers here. So there's 4 plus 6i, there's negative 2 plus 2i, there's 6 minus 2i. You can sort of plot these numbers here. What if we took these complex numbers, use those as the C term in our recursive diagram? And then note, when you use z as 0 and the constant being one of these numbers, what happens to the equation? Does it go off to infinity, or does it sort of stay put? You can make that determination. And here's what that looks like. For the red one here, for this complex number, you can see right there, that's the negative number plus the number times I, it doesn't go off to an infinity. We say that it's part of a set. You'll see the set here in just a second. The other number eventually zooms off to infinity. It's not part of the set. So we're just going to run all these numbers and try to determine which ones are going to sort of stay sort of like in a constant like this, which ones go off to infinity. This mathematical technique was sort of understood at the turn of the 20th century, but nobody could do it. You'd have to do innumerable calculations to be able to figure out anything. Mandelbrot was working at IBM in the 1970s and started using computers to be able to do this. And when he plugged this into a computer, he started to see a really interesting pattern emerge. These were all of the values of all the complex numbers that sort of stayed constant like this. All the others that went off to an infinity he didn't include. And you could already sort of see there was a weird kind of shape emerging. With more sophisticated computers, more sophisticated graphics, this is what he discovered. I've superimposed the complex number plane on here. Everything in black, all of those are those complex numbers. All of those are based on a calculation through this recursive equation, and all of these are numbers that sort of stay sort of constant. Anything outside here is something that goes off to infinity. Well, then he took the next step. What if we gave colors to everything that went off to infinity? We color that blue or something like this. This is the result. It's called the Mandelbrot set. All the numbers here, anything in black is a complex number that doesn't head off to infinity. Everything else heads off to infinity. I've included here a link to a YouTube video, which is I want you to watch this on your own, because it's really quite amazing. If you zoom in on any one of these areas, especially these areas here in that boundary between the blue and the black, well, I'll just let you explore it if you haven't explored it before. But I will say this, looking at the Mandelbrot set is like looking at something like a coastline or some other sort of complex shape in nature. Fractals maybe are more prevalent in nature than sort of regular Euclidean geometry. And the video I want you to watch next is by Ron Eglash, who's done some really interesting field work on fractals and fractal geometry in African design. And he makes some interesting claims about how in African culture there was a deep understanding of fractals maybe before any other cultures had sort of figured out the beauty and importance of fractals. So that's it for this lecture. Darwin and Joseph are going to now play the video. You have access to the video. I put this up on Karma, but we're going to watch it together right now. Then after we watch this video, we've got a design exercise planned that's going to involve fractals, and they'll tell you about that after the video. See everybody on Tuesday. I'm trying to stay as warm as I can here in Minnesota, and can't wait to talk about writing next week, next Tuesday.